rstanarm package, which we will be talking about today. If you would like to follow along with the slides or the code, anything like that, you can just go to this URL, bit.ly/rstanarm-share, and that should be a Google Drive directory that's publicly available on the Stan Group Google Drive, and you can download the few files that we're going to be using today. So I'll just go full screen here. This is, as Eric mentioned, an introduction to Bayesian computation using the rstanarm package. So first, just to get a disclosure out of the way, I'm an employee at Columbia, where I'm coming to you live this morning. I, along with Eric and a couple other people, are co-founders of Stan Group, which is a private company. And according to Columbia University policy, in this situation, those interests have to be disclosed to everyone during presentations. So if you have not yet installed the rstanarm package, it ought to be pretty straightforward. You can install it like any other R package. It's best to use repos, this cloud.r-project.org. That will redirect you to the closest mirror. It's good to specify dependencies equal true to get all the suggested packages that can be utilized by rstanarm. Unfortunately, we didn't quite upload the newest version of rstanarm to CRAN in time, so there's a little bit of a mirror disconnect. So when you do this, it may ask you if you want to install the 2.13.1 version from source, in which case most people, if you're on Windows or Mac, should press N for no, and it will install the 2.12.1 version of rstanarm. That's plenty fine for today. But if you're quite certain that you have a C++ compiler that's installed and configured correctly, as would be the case on a Linux system, then you could go ahead and press yes. But the safer option would be to just press no, install the package, the binary version of the package, and it should be plenty adequate for the things that we're going to do today. You just might later this afternoon or tomorrow want to reinstall rstanarm so you have the latest version. The only things that are going to be different between the two versions today are possibly the way some of the plots look after you start to see the output. Anyway, other than that, it's a pretty straightforward installation. First, I want to talk a little bit about what is Stan. Like Eric said, this is the second of two webinars that we had. The first one with Andrew Gelman, maybe many of you saw, but perhaps some of you didn't. So I want to talk a little bit in general about what is the Stan project. And Stan actually means many different things. First, Stan is a new computer language. Specifically, it's a probabilistic programming language that helps you express models statistically and with probability. So in this sense, it overlaps a good bit with R. It's more focused than R. In R, you can do a lot more things. But basically, Stan overlaps a lot with the statistics and the distributions part of R, like all the D norm and R norm and things like that. That's where Stan and R overlap a lot. So Stan is its own high-level language for expressing models using statistics. And Stan also comes with a translator of high-level Stan syntax to C++ that then gets compiled. So you never really have to look at the C++, and today we're not even going to get into Stan syntax at all, but behind the scenes, that's what's going on. And the C++ links to the Stan math library that includes both matrix operations and scalar operations, all of which support what's known as auto-differentiation. If you're not familiar with auto-differentiation, it basically means it allows the C++ compiler to figure out the chain rule from calculus. So if you need the gradient with respect of some function with respect to the parameters, auto-differentiation can provide that for you, It's a lot of work for the compiler, but very little work, no work at all actually for the user. And you can use algorithms that depend on partial derivatives or gradients of the parameters for some function. And so Stan also includes new gradient-based algorithms. It also includes some older gradient-based algorithms as well, all of which are intended for statistical inference. Today, we're going to be focused on a new algorithm that facilitates Bayesian inference, but you can also use Stan for some non-Bayesian statistical tasks. Stan also includes high-level interfaces to all of the Stan functionality, such as the rstanarm package and other ones that we're going to see today, but you can actually access Stan from Python, from Julia, and other high-level software. Stan includes post-estimation functions. A lot of these are more fully developed in R, and we'll see these today for visualizing the output of your analysis and so forth. Stan also includes a large community of users and many developers. So if you're interested in contributing to rstanarm or Stan in general, or just using it and you have a question, there's a lot of people out there on our website that can help you. So that's, sort of an overview of all of the pieces in Stan. Now, what specifically is the rstanarm package? The rstanarm package is an R interface to a handful of models in the Stan language that have already been written, mostly by me and by Jonah Gabry, who's the other co-author of the rstanarm package and also a co-founder of Stan Group. And these pre-written Stan programs have already been translated into C++ and compiled on the CRAN servers, so all you have to do, as was mentioned previously, is install the package, and they are ready to be executed, and you can use Stan in the back end with using the Stan estimation algorithms without having to worry about the Stan syntax or the compilation step, anything like that. So the syntax in the rstanarm package is deliberately chosen to mirror that of popular model fitting functions that are already in R. So in order to use the following functions, all you have to do is load the rstanarm package and prefix them with stan underscore. So I imagine everyone who's familiar with R has been exposed to the LM function for estimating linear models with continuous outcomes. To estimate a model with the same likelihood and the same syntax using Stan, you just call the stan underscore LM function. And the same convention holds for all of the other R functions that are imitated with the rstanarm package. So there's the AOV function for analysis of variance, GLM for generalized linear models, and also generalized linear models with a negative binomial likelihood that is available in the mass package. Both of those have corresponding stan underscore versions in the rstanarm package. In addition, the stan underscore POLR is similar to the function in the mass package for estimating models with ordinal outcomes using a proportional odds assumption. If you're familiar with the LME4 package, the stan has analogs to the Elmer function and the Glimmer function for specifying models that have group-specific terms. This is a very attractive feature of rstanarm, although we're probably not going to have time to get into too much of that today, but presumably we'll take that up in a future Stan Group webinar. Finally, there's the GAM4 function, which there's a Stan equivalent for in the rstanarm package. This may be less familiar to a lot of people, but it allows you to estimate a model, a generalized linear model that not only has group-specific terms with the LME4 syntax, but you can also use splines as part of the model and use it in much the same way that you would use splines with like the MGCV package, etc. So all of these, the syntax in the rstanarm package is going to be the same for the first few arguments is all of these model fitting functions in R that you're probably already familiar with many of them. And then there are some additional arguments that are specific to Stan, but most of those have defaults already. And so the rstanarm package allows you to use Stan to get up and running quickly with Stan, to get familiar with the process of doing Bayesian estimation, diagnosing the model, looking at predictions of the outcome without having to know the Stan language. But if you're interested in learning the Stan language, then it's a fairly straightforward step to go from the rstanarm package, which has a few precompiled Stan programs, to using Stan directly, where you could estimate almost any model that you want. But for the ones in rstanarm, if you're sharing it with other colleagues, it's pretty convenient. It has fairly minimal installation requirements compared to Stan as a whole. So we'll be talking about the rstanarm package, in particular the GLM function, in more detail today. So as I mentioned, you can use Stan for Bayesian inference, for non-Bayesian inference. I think it adds the most value from a Bayesian perspective, and that's the one that we'll mostly be focusing on today. And one of the things about Bayesian inference is it fits very directly with what's known as Bayesian decision theory. So as I mentioned, I work at Columbia and also for Stan Group, and one of the things that becomes pretty obvious if you're in both of those worlds is that quantitative estimation differs in some respects, whether you're doing academic research or whether you're in the private sector, government sector, nonprofits. In academic research, the models tend to be a little bit more complex, but that I don't think is the real important distinction. The important distinction is that when you're doing academic research, you're rarely using those estimates to make some potentially costly decision, whether that's a business decision or a policy decision, what have you. Whereas businesses are using these estimates, these quantitative models, to make decisions that, for simplicity, we'll assume are intended to maximize expected profit. So, calculating the costs and the benefits of a menu of decisions. Now, you can generalize this to maybe risk-adjusted profit or something like that, but just for simplicity, we'll think about a profit function, but it's expected profit function. You don't know all the details about the data generating process. You don't know what's going to happen in the future with, maybe other competitors, with your supply chain, etc. So there's a lot of uncertainty, but when you take the expectation of profit, that essentially averages your uncertainty over the various unknowns and allows you to make decisions that are rational under some reasonable axiom. So I talked on the previous slide about taking expectations to average over uncertainty. So what are those sources of uncertainty? The first is model uncertainty. What models should be used for this or that data generating process? The second source of uncertainty is parameter uncertainty. What are the parameter values in the models that you think are candidates for understanding a particular data generating process? Third source of uncertainty is what I call systematic uncertainty. What system of reasoning should be used to evaluate the implications of the models, or at least the subset of models that turn out to be good? And the fourth source of uncertainty is unfortunately a fact of life, but it's something that everybody has to deal with. Does the software that you're using successfully do what it's intended to do, which is to say, estimate the parameters among the good models? And you have to consider those four sources of uncertainty when doing an analysis and possibly making a costly decision on the basis of that. So the Bayesian approach neatly accounts for the first three. In particular, for systematic uncertainty, a Bayesian approach always uses probability as the system of reasoning. So the model uncertainty and the parameter uncertainty are expressed in terms of probability. Then there's still software uncertainty, but we're pretty confident that Stan substantially mitigates for software uncertainty because it works pretty well, or at least can be made to work pretty well. There's other approaches to quantitative analysis out there. These days, there's a lot of things going under the name supervised learning. These also sometimes have a Bayesian motivation, but they sort of don't deal with uncertainty in as an explicit way. So the supervised learning approach generally isn't going to take any particular stand on what system of reasoning you should use to analyze the results. It's often applied to very large data sets where if you're estimating a right model, there's not much parameter uncertainty. But supervised learning approaches typically are going to ignore uncertainty in the parameters and focus on the choice of the best model. So dividing into training and testing data set, estimating a model with the training data set and seeing what predicts best in the testing data set. But you might find yourself in a situation where one model predicts a little bit better than another model, but you don't know if that is just an artifact of the particular testing data set that you're dealing with or something that holds more generally. You might want to make a probabilistic statement about that, but most of the lasso software and things like that don't go there. Finally, there's the frequentist approach. It also uses probability to reason about the implications of good models, but it interprets probability in a different way. It interprets it as uncertainty over the estimator if the estimator were applied repeatedly to independent samples from the same population. And that metaphor is something that is perhaps relevant for survey sampling and government purposes, but doesn't seem to have a lot of credibility for business decisions where you're not going to sample many times. You probably aren't even sampling at all. You just have the one set of data that you have and you want to make inferences about that. In any event, the frequentist approach doesn't really quantify model or parameter uncertainty in the same way, the same intuitive way as the Bayesian approach. In order to update your beliefs in the Bayesian paradigm, you need four things that sort of capture this uncertainty. First is you need a probability distribution for the data generating process. So to say, this is normally distributed, this has a Bernoulli distribution, etc. Then you need a description of your current beliefs about those parameters, also using probability distributions. So if you have a regression model, it has regression coefficients, you need to specify your beliefs about those parameters and express it with the language of probability distributions. So for there, you might want a distribution that has heavier tails than a normal distribution. Student T would be an example of that. The third thing you need, obviously, is data. Although from the Bayesian perspective, the data that you have doesn't need to be a random sample from any population, like all adults in the United States, because the Bayesian inference is solely conditioned on the data that you have, not evaluating the implications of what if we were to do this over and over and over again. Fourth thing you need to be a Bayesian is an algorithm, in particular an algorithm that does what's known as Markov chain Monte Carlo, to draw from the implied posterior distribution, which is implied by 1, 2, and 3. So STAN is an algorithm to draw from posterior distributions. It does so very well for posterior distributions that are differentiable, but it's on the quantitative analyst to do 1, 2, and 3. The rstanarm package makes it a little bit easier to do steps 1 and 2 by providing a menu of choices, but certainly you need to obtain data that is reasonably consistent with the choices that you make about the data generating process and expressing your beliefs about those parameters in that model. So all this together constitutes what we call the Bayesian workflow, which, steps 1 and 2 specify a joint distribution for the data and unknowns. That's the product of steps 1 and 2 on the previous slide. that constitutes a what we call a generative model. And a generative model is one that you can simulate data from. And this is a very important step for everyone, but not everyone takes the time to go through this process of simulating data and then fitting the model on the simulated data to verify that the software is working appropriately, that you can recover the parameters with sufficient accuracy, etc. So before you start to use your real data, it can be very helpful in a lot of respects to fit a model to data that you've simulated based on what you believe the data generating process to be before you take into account the actual data that you've collected. But once you're satisfied with that process, you can fit the same model to real data, again drawing from the posterior distribution of the unknowns, unknown parameters, etc., conditioned on the known data that you have collected. When we get draws from this posterior distribution, that we can then analyze to evaluate the model or to make conclusions. But oftentimes we find when we go through this process that there's something about our model that is lacking, that's not doing particularly well. And this is usually pretty apparent from some of the plots that we can make. And so you might want to go back and start the cycle all over after adding additional structure to the model, maybe allowing the parameters to differ from one group to the next as in a hierarchical model, etc. But once you have a model that you're pretty happy with, you can draw from what's known as the posterior predictive distribution. This is a distribution for what you believe future data will look like given the model, given the data that you've collected so far, and given the beliefs that you came in with about those parameters from the outset. And this is a very important concept, this posterior predictive distribution, but one that people seem to have kind of a hard time grasping because it's pretty unique to the Bayesian setting. So for any observation, you can get a full distribution for quantifying your uncertainty as to what you believe future data would look like if it was generated from this model. And these posterior predictive distributions are basically like data. You can query them like data. You can calculate functions of them in order to make a business or policy decision. And so under the model, under this condition, under that condition, you know, we expect profits to be this and costs to be that. What's the decision that we can make that gives us a distribution of profit that we're happiest with? And that distribution, you know, some distributions have a higher mean and a higher variance. You may prefer to have lower variance even if it lowers the mean, etc. All of these things you can do with the posterior predictive distribution. And so for the rest of the day, we're going to be basically talking about aspects of this Bayesian workflow and doing it in rstanarm, which allows us to fit the model to the data quickly without having to spend so much time coding it ourselves in the Stan language, because that's already been done for you. So we're going to use today an example with data that comes from the website lendingclub.com, or the company Lending Club. So I should say in advance, I don't have any connection to Lending Club. These data are publicly available, but I'm certainly not trying to change their stock price or anything like that. So we're going to be using their oldest data that's, you know, several years old now, and applying a pretty simple model to it. So none of this is really intended to influence your decision as to whether you want to borrow money or lend money through lendingclub.com. So if you followed the link that I was referring to before, there's a file in that directory called get_data.r, which if you have in your working directory, you can source. It downloads the data from the lendingclub.com website, does a little bit of processing to it, and we have a data frame that consists of some 38,000 people, and it has 7 variables, some of which we'll be using in the model. And for to make this run a little bit faster, I separated this into training set and testing set. But there's no reason from a Bayesian perspective why you really need to do that. We already have the capability to penalize models so they don't overfit too much in the training data. We also have the ability to do model comparison just based on the data without having to separate it into training or testing. That gives us more observations to condition on to get more precise inferences in the posterior distribution about the unknown parameters. But you know, to make it run a little bit faster, we're just going to estimate the model on the training set today. And you can look at the distribution of the outcome variable that I've created, y. This is a factor that has two levels, problem and no problem. So these data are from people who've been accepted, several years ago were accepted to get a loan through lendingclub.com. And then the question that this y variable pertains to is, did the person have a problem paying back the loan? There were 1,558 such cases of that where they were, you know, they defaulted on it or they didn't pay all of it back, something like that. And then many more cases where the person who received the loan, you know, made the payments every month and eventually paid the whole thing off. And so those are coded as no problem paying back the loan. And so from a perspective of a business like lendingclub.com, you definitely want to be interested in the probability that someone is going to be able to pay back the loan in order to make decisions as to whether this person should be offered a loan, and if so, at what interest rate, what, you know, other terms in it, etc. So we're going to be modeling this binary outcome of whether the person has, you know, essentially defaulted on the loan or not. There's a number of predictors in the original data set, actually hundreds of predictors available in the raw data. We're just going to focus on a subset of those. So two of the continuous predictors that you might think are particularly important for predicting whether someone is going to have difficulty paying back a personal loan are the loan amount, and you can see the summary statistics for the loans being offered in this group of people, and also the stated annual income of the person who received the loan. And so intuitively, if the loan amount is sort of large relative to the person's income, then they're going to have more difficulty making the payments. There's also a number of binary predictors. Here we're focusing on three. First, there's a variable called employment length, which is coded as 0 if the person was unemployed at the time that the loan started. So that would seem to make it more difficult to pay back the loan. There's also the term of the loan. So for lendingclub.com, that can either be 3 years or 5 years. And there's a variable about the home ownership status of the person receiving the loan. So I discarded the observations where the person reported not having a home or some sort of other. Both of those were extremely small number of observations to focus on three categories. Does the person have a mortgage? Does the person own their home outright? Or does the person rent their place of residence? And that can vary by, you know, all kinds of things, and presumably a lot of it is correlated with their annual income and things like that. So these are the predictors we'll be using in the model. So to get started, if you've installed the rstanarm package, we can do just conventional R, load it with library rstanarm, and that will display the following messages. And these should be heeded pretty carefully. So the first is to not expect the default arguments for the prior distributions to remain the same in future rstanarm versions. And so almost all of the functions in rstanarm will have some default argument for the priors on the parameters in those models. And we've chosen defaults that we think are pretty appropriate for wide usage. However, this is a subject of active research, and we may very well change our minds as to what's the most appropriate default prior for a particular model in later versions of rstanarm. So if you're writing an R Markdown file or you're writing a script that uses rstanarm, it definitely behooves you for reproducibility to specify those priors explicitly in your script, even if you're just using the same priors that are the current defaults. So if you specify those explicitly and you come back and estimate your model again in 2 years, it'll be using that same prior, even if the default in rstanarm has changed by that time. So it's good to specify those explicitly if you want your code to be kind of future-proof. I don't think we're gonna. It's very unlikely we would take away an entire prior family. So your code will probably still work, but we might have a change of heart as to what is the best default prior, you know, a couple of years down the line. The second thing that it tells you when you load the rstanarm package is that if you're, you know, doing this on your own laptop, most of those have multiple cores these days. As long as you're not running out of RAM when you do so, we recommend that you execute the analysis in parallel. So Bayesian analysis, at least responsible Bayesian analysis, is going to run what's known as multiple markup chains, and by default that's going to be 4, and one of the things that you want to check is whether those have converged to the same distribution. Stan and rstanarm for these models is really good about doing that. It'll give you a warning message if it seems that something has gone wrong, but if you have to execute 4 chains in serial, then it takes almost 4 times as long than if you can execute 4 chains in parallel. So as long as your computer has more than 4 cores on it, you would be able to do all the chains by default in parallel, and that'll go a lot faster. So to use as many cores as are available on your machine, you can just call the little bit of R code, one line, at the bottom of the slide to set the mc.cores option equal to the number of cores that is available on your computer, and that's appropriate as long as you're not swapping and running out of RAM. So that's a good option. Another thing that we, like I was saying before, it's a good process to go through is to think about how the process might be generated. So in this slide, I have a particularly simple model for whether the person will have probability paying back the loan. So I'm going to use the training data set and draw from a Bernoulli distribution, which is just a binomial distribution with one trial, so size equal 1. And I'm going to use a different probability for each person or different groups of people in the data set. So what this line with the prob argument says is that if the person's employment length is 0, which is to say they don't have a job at the time of the loan, I'm going to assign them a 0.5 probability of defaulting on the loan. But if the person has a job, which is to say employment length is greater than 0, then I'm going to assign them a lower probability of defaulting on the loan, specifically 0.1. And so if I execute the chunk at the top and then look at just the frequency table of the simulated values for loan default or not, we get some distribution like this that you might be able to work out in this simple case, but in more complicated cases, it might be sort of difficult to know analytically what the distribution of your outcome looks like under your assumptions about the data generating process. So this seems perhaps reasonable, even though it's simplistic. And then I could, if I wanted to, and you should want to, fit your model to the simulated data to make sure it's working well. And so we could do this with a call to the stan_GLM function. Its first argument is a conventional R formula. So here I'm specifying that the outcome, or at least the linear predictor of the outcome, only depends on one variable, which basically amounts to does the person have a job or not at the time of the loan. I could specify a data frame that contains these, but I didn't in this particular situation. I will in the next slide. Since this is a binary outcome, we need to specify the family argument the same way we would with regular GLM. So we use the binomial family, the default link function, which is the logistic link function, to estimate a logit model for this outcome, and using normal prior on the coefficient on the job variable, a normal prior on the intercept to this generalized linear model. The normal distribution is the default for both of those, and internal to stan_GLM, it does some rescaling, so to basically make the standard deviation of these priors a function of the standard deviation of the predictors in the data. But this is sort of a minimal syntax that would estimate the model, and if you specified the thing about cores on the previous slide, it would run these in parallel. So I've done this once. I know the stan_GLM function will work perfectly well for a model this simple, and then you could start to go on to a more complicated data generating process where you might consider not only does the person have a job or not, but how much income, how much is the size of the loan, those sorts of things. Simulate data under that process, fit the model again, verify it's working correctly before you go on to estimating your model on the actual data, in this case the data from lendingclub.com. So here I've used the same setup, again calling the stan_GLM function with family equal binomial and link equal logit to estimate a logit model. These variables that appear in my formula that goes to stan_GLM all live in the training data set, so I specified that as the data argument. And so let's think more carefully about what formula we're using here to specify the linear predictor and a logit model. So we're saying, you know, the log odds of defaulting on the loan are a function of the logarithm of the loan amount. The term variable, which is a two-category factor variable, whether it's a 3-year loan or a 5-year loan. The home ownership variable, which is also a factor. It's relative to the people who have a mortgage. So 2 dummy variables will be created, one for people who own their home outright and another for people who rent. And then continuing with the formula, we also include the logarithm of the annual income of the borrower and a dummy variable indicating whether the person has a job or not at the time of the loan. So just like in regular GLM, if you pass a factor variable, it'll get expanded into dummy variables, excluding the reference category. If you wanted to use interaction terms, those could all be specified in exactly the same way as you would with stan_GLM. And in particular, the stan_GLM function uses the exact same likelihood function as in GLM, and so it supports everything that GLM supports, but adds some additional arguments due to the fact that we're going to use Bayesian estimation, Markov chain Monte Carlo, to draw from the posterior distribution rather than obtaining a point estimate through maximum likelihood. Consequently, Stan needs to know what prior distribution you want for the parameters. Again, these are the default priors, and so when you say prior equal normal, that's saying that you want a normal prior that has prior expectation of 0 for each of the coefficients that are implied by the formula for the linear predictor of your model. Now, the normal function can either take a scalar for its location, by default that's 0, or it could take a vector which is equal in length to the number of coefficients being estimated in the model. So in this case, we have 1 for the loan amount, 1 for the term of the loan, 2 for the home ownership variables, 1 more for the annual income, and 1 more for whether you have a job. So whatever that adds up to, you could specify a vector of that length, giving your prior expectations under a normal distribution for this process. There's also a normal prior. This is going to be a scalar on the intercept to the model, which is by default included in these formulas unless you explicitly take it out by including like -1 or something in your formula. So you can, with the normal distribution, you can specify both the prior location and the scale. You could easily use student t distribution for the priors. We have some other priors known as hierarchical shrinkage that we're not going to get into today, all of which are possible, although the normal distribution is the default. However, in rstanarm functions, if you're not going to specify informative prior beliefs about the coefficients, which is to say, you know, you're happy with a prior expectation of 0 and not too worried about, you know, what the prior scale is, it's really useful to specify the additional argument QR equal true. I don't want to get into too much details about that, but basically this does a reparameterization of the model, which makes it much easier and much faster for Stan to draw from the posterior distribution of the unknowns, and then behind the scenes it reverses the transformation after the fact so that you get a posterior distribution that is in the parameterization that you specify with the formula to Stan JLM. So we utilize this QR reparameterization a lot, and if you're interested in more details about it, you can go to the vignettes section for rstanarm, and it's talked about in a couple of those vignettes. But basically, if you don't have an informative prior on the parameters, then using QR equal true is almost always going to be your best option. So we can estimate this. It'll probably take about a minute if you're running it on your computer with multiple cores, and then you could print this out and you get numerical output that looks similar to what you would do if you estimated the model with GLM and called summary on it. But rather than look at the numerical output, it's possible in rstanarm to get a graphical representation of the posterior distribution, and this is what I want to focus on first. So there's a plot method for the objects produced by the fitting functions in the rstanarm package. Here I'm saying I only am interested in a subset of the variables, or more specifically the coefficients, on a subset of the variables, and the plot function produces a ggplot object, so you can assign this to a symbol and do all sorts of things with the ggplot2 syntax to change the look and feel of the plot. But by default, it looks like this. So we've specified in the call that we want uncertainty intervals of 0.8. So basically what this means is the sort of thick blue lines constitute an interval for which we believe, based on our model, conditional on the data, that the true coefficient lies within the dark blue interval with probability 0.8. Now that's not a statement that you can make validly in the frequentist perspective. It's not a statement that follows from anything that you can do with like lasso or whatever if you're just doing optimization. This is a particular characteristic of Bayesian estimation that allows us to make probabilistic statements about unknowns conditional on the data. And so we, on the basis of this, think there's a percent probability that the coefficient on the loan amount falls in this sort of positive range on the horizontal axis here. So we're pretty certain that, having a larger loan amount increases the probability that the person will have difficulty paying it back. The light blue circles here are posterior medians. So that is the value such that conditional on the data in our model, our initial prior beliefs, there's a 50-50 chance that the true coefficient is lower than this, 50-50 chance that it's greater than this. You can see a little bit of an extension on these with like very thin lines. Those constitute a 95% interval. So there's a 95% probability in our belief system that the true coefficient falls within the edge of these little lines here. So the little lines are more prominent on this, the coefficient on the home ownership variable. So again, the dark blue line is a 80% interval. We believe that the coefficient on the home ownership variable falls within this interval with probability 0.8. This interval straddles 0, so we're not particularly certain as to whether this coefficient is positive or negative, but it has a much wider interval, and that's due to the fact that in this data set there are not very many people who own their home outright. Most of them are younger and so forth, and so we have less certainty about that coefficient than we do on some of the others. So if you just print the post object, you get a lot of the same information, but seeing it in graphical format, I think, emphasizes the real Bayesian nature of the output. You get a distribution rather than a point. And there's lots of plots that we can make. So I'm going to switch now to RStudio and use a web app. So you can call this with launch shiny stan and just pass it an object that's produced by our rstanarm function. It will take a second to run, but it should eventually open up a web browser, a way for you to make even more plots and other diagnostics and so forth that you can use to interrogate your model, see if there's any warning messages. So here we go. So this will open up on a random port on your system, and then there's a web app that provides access to it. So the first thing we might click on is the diagnostic tab. If you're familiar with Bayesian inference, this is a trace plot, the evolution of the Markov chain over the iterations. We have one chain for each color, and these all look pretty good. In particular, there's no warning here about divergent transitions. If there were, there would be large red points over around here and other of the diagnostics. In this case, there weren't any, so we're not going to worry too much about that. But if you're fitting your own Stan models and a warning comes up about there being divergent iterations, that's a problem to take seriously. There'll be a link in the warning message that you can click on to go to the Stan website that's going to have more information about that. But also in the Shiny Stan web app, there's a glossary that defines all of these terms. So if you want to learn more about what a divergent transition is, or R hat, or anything like that, all that information is provided in the glossary. We can also get convergence diagnostics. So R hat is one of the more popular ones. You want that to be close to 1. And in this case, all of the R hat values for the various parameters were very close to 1. So that wouldn't be a problem. When doing Bayesian analysis, there's an important concept of the effective sample size that you've drawn from the posterior, in contrast to the nominal sample size, which by default is going to be 4,000 with Stan. So the effective sample size is the size of a sample, an independent sample, that would give you the same precision in the estimates of the posterior mean as the sample from the posterior distribution that you have. But the sample from the posterior distribution that you have is not independent draws. And so there's inflation to the variance there. And so it's more appropriate to look at the effective sample size. But in this case, all the effective sample sizes, except for one parameter, are very close to the nominal sample size. And that indicates there's very little dependence in the draws. That can also be assessed with autocorrelation plot. So the zero order autocorrelation is always 1, but it falls off very quickly after that. So this is something that Stan excels in. It tends to get draws that have very little dependence, in contrast to some other Bayesian estimation procedures that you might be familiar with, such as Gibbs samplers, that you may need to run for like millions of iterations because the dependence among the draws dies out so slowly, and you need a lot of draws in order to make precise inferences about posterior means, as compared to Stan, where you only need like a few thousand, particularly if you have such little autocorrelation as is exhibited here. Finally, there is a tab called PP check, which does what's known as posterior predictive checks. And this is a little bit more automated with the models in rstanarm. So in the blue line here, we have an estimate of the probability of default just based on the frequencies in the data. And the light blue lines, which you might have a little trouble seeing over the GoToWebinar thing, are 10 realizations from the posterior predictive distribution of the same quantity. So insofar as the lines, the thin lines, which are those implied by our model, are similar to the dark blue line, which is the line implied by the data overall, then we are increasingly confident that our model is fitting the observed data pretty well. And that's the case both for people who have a low probability of default and for people who have a higher probability of default. So there's lots of tabs that you can calculate here. So this is an example of calculating the average default probability. That's about 0.18. That's the dark blue line. And then we have a bunch of simulations from the model where it also calculates the average probability of default, and we can make a histogram of those. And we can see here that this model is at least capturing the marginal mean pretty well because it falls right smack in the distribution of the histogram. But the histogram is important because it quantifies our uncertainty about the overall probability of default. So in the training data, it happened to be about 0.18, but on the basis of the training data, any number between 0.15 and 0.19 has, a decent chance. Numbers lower than 0.15 or greater than 0.19 have a pretty small chance, but it is still positive. And the same thing can be done on the standard deviation. The minimum and the maximum, none of those are particularly relevant when the outcome is binary. But doing these checks to make sure that your model is fitting the observed data well is something that is important to do. So if that is satisfactory, we can go on and look at the estimates. So here we can see a plot that is similar to the plot that I was making before. It just has different colors. If you want to see the numbers, there's a tab for that. If you need to generate a table in Tech, you can do so. There's some other exploration, that additional graphs that it can make. So that one's not particularly exciting, but if we go to the annual income variable, this is a depiction as to how much instead, let's do it like this. Select annual income for the horizontal axis, and we want to put the value of the log posterior distribution on the vertical axis. When all goes well, this should indicate kind of a curved relationship. Each of these dots are a realization of the posterior distribution, and as I was saying or actually I don't think I said this, but it's pretty intuitive, that most of these draws are in the negative range, indicating the more income that you have, the lower probability you have to default on the loan. We can make three-dimensional plots of different parameters, rotate them around with a WebGL interface. Lots of things can be done with ShinyStan. In particular, you might want to check out the glossary that has definitions for all of these terms that I've only briefly talked about. And so we can close down the web app, shut down that tab, and control is returned back to our R session. So one of the questions that we're often asked is, do the priors make a difference in this model? Or, what were the priors? How sensitive is the inference? And so we've implemented a plot called posterior versus prior that you can just call on an object produced by the rstanarm functions. Again, it has a probability argument, so you can say how wide you want the posterior intervals to be. You can also select a subset of the parameters. You can even do that by a regular expression. So here I'm saying I only want to look at variables that start with H. In this case, they're the two home ownership variables, but I could have looked at any variables that I want. And what this posterior versus prior function does is that at first it goes back to the model and just draws from the prior distribution that you specified without conditioning on the data. And so here we have pretty wide 50% intervals for both of these variables, before the data are taken into account. The interval is a bit wider for the home ownership variable, and that has to do with the fact there's many more people who rent, many more people, both of these are relative to people who have a mortgage, but there's more people who rent in this data set than own their home outright, and consequently the prior interval for the rent variable is a bit smaller, but still, pretty wide. It has a 50-50 probability of being between -4 and 4, 25% probability of being lower, 25% probability of being higher under the priors that we specified. And so that certainly is only a weakly informative prior. Basically on the log-odd scale, it's entertaining basically all reasonable values, and perhaps some values that aren't even reasonable. But when we condition on the data and we get the posterior distribution, we get the same intervals, but actually the 50% intervals in this case are less than the diameter of the little circle, which is indicating the posterior median. So if we'd had less data, you would actually see some small lines poking out from these indicating the 50% intervals. But basically, in this case, we have a lot of data. It's very informative on these two variables. And our posterior beliefs about these two, conditional on the data, are that they have very small coefficients, very close to 0. The rent variable is maybe a little bit higher than the home ownership variable, indicating people who rent have a slightly higher probability of defaulting on their loans. So that is a good way to quantify how your beliefs have been updated. And there's also a prior underscore summary function that you can call that'll give you a numerical and text description of what the priors were actually used when you called one of the models that's available in the rstanarm package. So having done all this, if we're a company like lendingclub.com, we might want to assess, what is the characteristics of these portfolio of loans that we're making on. So just for simplicity, I'm going to assume that if the loan is defaulted on, then the lender doesn't, pay any of the interest and you lose, the whole loan amount. But if the loan is paid back on time, or eventually paid back, then you get the interest payments. These interest payments are pretty high. relative to interest rates in the past few years, and so we want to see how much profit is at issue, and so we can first call the posterior underscore predict function, which will get us realizations of what we believe the outcome to be in future data. So here I'm going to pass the testing data set. The model was estimated on the training data set, but you can specify a new data argument to posterior predict, and we want to obtain 500 draws from the posterior distribution. These will be either zeros or ones, which simulates whether the person defaults or not, conditional on our model having updated our beliefs about the parameters using the data available in the training data set. And then what I do, you don't need to understand the details of this function. I just calculate the profit or loss that's implied by each of these realizations from the posterior predictive distribution. So if the person is simulated to default, then we're going to assume we lose the entire loan amount. If this is simulated as 0, then we calculate up the installment payments multiplied by the number of payments, and then subtract the original amount to basically tell us the accumulated interest. And then we can make a plot of that, here normalizing it by the amount being loaned out, to see what is the expected distribution of profit margin on loans like this. And as I was saying, these loans are a pretty high interest rate, and they loan to a lot of people. So if you aggregate over the whole portfolio, a few people are going to default, but that's overwhelmed by the majority of people who pay back the loan on schedule. And consequently, you can get an expression, here a histogram, distribution for the profit relative to value at risk, basically. And so here we see a histogram. It's pretty tight, around 0.5, and so if that was the correct model, you would be pretty happy with loans like this. So as I was saying before, this is a pretty simplistic model using old data. It doesn't take into account systematic factors like what if the economy goes into another recession and lots of people suddenly have to default, things like that. So this is perhaps a little bit optimistic, but it's the sort of thing that you can do as a business to make decisions. Do we need to hedge this portfolio, etc.? How much? And in order to do that, you need to have a full distribution of uncertainty, not merely a point estimate for what's the most likely thing to happen, but what are possible things that could happen that might be better or worse than a central scenario. And the Bayesian process automatically gives you that for any quantity of interest, and then you can plug that into some profit function and make business decisions off of that. Another thing that is particularly easy to do with the functions in rstanarm is to use model comparison. This is using a function called lu and a package called lu that is geared toward model comparison. So I might estimate a second model. I can use the update function to that, and this basically says estimate the same model but take away the variable that pertains to whether the person has a job. And so we can then compare the original model and the second model using the lu function. So what the lu function tells us is basically if we were to leave each observation out and re-estimate the model and then predict the left out observation, what would be the expected log predictive density of those sequence of leaving one out and then fitting the model and predicting. Now in practice, it doesn't actually leave anything out. This quantity can be estimated under one assumption just from the model output that we obtained originally. And that assumption is that no observation has an overly influential effect by itself on the posterior distribution. But that assumption is something that is actually readily testable with what's known as the Pareto K estimates. So if any of those are above 0.5, particularly if they're above 0.7 or 1, that suggests that there's an observation that is having outsized influence on your posterior distribution. And if that's the case, for just a few observations, it'll give you a suggestion as to how you can call the Lu function, actually leaving out those few observations, estimating the model, again obtaining the posterior distribution with the remaining observations, and actually doing the prediction. But in this case, it says all our Pareto estimates are okay, so we don't actually have to leave anyone out in order to estimate what the expected log predictive density would be if we were to leave out each observation in turn. And we get a number here that's only important in relative terms. It's like negative 4,100 or 117. We also get an estimate of the effective number of parameters. So the effective number of parameters takes into account that we provide some prior information when we specify the model. So you if you go back, you can see we're actually estimating 7 coefficients, so that would be the raw number of parameters, but we provide a little bit of prior information about each of those, so the expected number of parameters is 6.4. This ELPD underscore Lu, which stands for expected log predictive density under the Lu process, already takes into account the effective number of parameters. So you can just look at the ELPD Lu and compare one model to the other. The model that has the higher expected log predictive density is expected to predict better in future data than models that have lower values. So in this case, we see the model that we estimated that takes away the job variable has a slightly larger value for ELPD Lu, but really it's very similar relative to the standard errors, and there's a compare function that you could do this that actually will give you the standard error of the difference. But the bottom line is that both of these models are expected to predict future data about the same. Sometimes there's a greater difference, and you can say more conclusively that this model is better than that model, but in this case they're pretty much equivalent on this criterion. You can also look at Lu IC, which is literally -2 times ELPD underscore Lu, but the Lu IC is in the same units as other information criteria that you may be familiar with, like the AIC or the DIC or the WAIC, etc. So for Lu information criterion, you prefer a model that's smaller on that value, which in this case the second model is, but only slightly and negligibly relative to the standard error. So we would say both of these models are probably about the same in their ability to predict future data. So just to wrap it up before we take some questions, we've learned a little bit about Bayesian theory and the workflow and the process that you want to go through to get posterior distribution and then analyze functions of posterior distributions. We estimated a model using the rstanarm package, but there's lots of other models that could have been estimated with rstanarm. So you can use any of the link functions that are available in GLM. You don't have to use binomial. You could also use Poisson if your outcome is a count. You could estimate linear models with Gaussian errors. You can do that with stan underscore GLM or stan underscore LM. You can estimate models that have hierarchical structure and group-specific terms using the stan underscore LMER function or the stan underscore GLMER function. The GLMER version is more appropriate when you have a non-Gaussian likelihood. We also have variants that of all of those functions that work with a negative binomial likelihood. And like I was saying at the beginning, rstanarm has support for a GAM4 style model, which includes everything you can do with the LME4 style model with the group-specific hierarchical structure, but also includes splines that you can put into your formula in much the same way that you would do with the GAM4 package or the MGCV package. We looked at plots of the model output, so you can just generate those with functions in the rstanarm package, or you can load up the ShinyStan web app and click through them automatically. The ShinyStan web app is really popular. It basically shows you everything that you want to look at. In particular, the first part about diagnostics, both if there's any warnings about problems that may have gone on during the sampling with divergent transitions and so on, and posterior predictive checks, where we can draw from the posterior predictive distribution and compare it to the marginal distribution of the outcome or some function of the marginal distribution of the outcome to see if our model is fitting the data well, and if it's not fitting the data so well in some part, we at least know that, and we might take some steps to go back and change our model, go through the whole process again. We used the posterior predictive distribution this time on testing data to calculate, sort of profit relative to risk, things like that can be, given to executives to make business decisions that take into account the uncertainty that you have about this unknown data generating process, and future values, and uncertainty about the parameters, uncertainty about the model, all those four sources of uncertainty. But hopefully Stan at least minimizes the fourth, and in particular the functions in the rstanarm package, which only expose a subset of what can be done with Stan, are very reliable, but you still want to check. And as I alluded to at the beginning, the rstanarm package makes it convenient to estimate a few, albeit very popular models, but almost any model can be estimated using Bayesian methods if you can express it in the Stan language. And if you're familiar with R, then the Stan language probably will come reasonably naturally to you, and then you have basically the capability to estimate any model, and to do it with Bayesian MCMC techniques, and to do it with Bayesian MCMC techniques that are particularly reliable. If there's a problem, there'll be a warning message about it, but for the most part, there's a lot of complicated models that aren't too difficult for Stan, and it can get draws from the posterior distribution that have minimal dependence between them, and so you only need a few thousand in order to make solid inferences about the data generating process. So we'll take questions in a second, but if you want some links as to where you can go to get started with Stan or to get more help, there's a textbook came out in 2016 by Richard McElreath called Statistical Rethinking that is based on Stan. It uses Richard's package called Rethinking rather than rstanarm, but it's very good for illustrating a lot of the concepts that we've talked about today. Andrew Gelman and Jennifer Hill will be coming out with a second edition of their applied regression modeling textbook, and the second edition is going to be using rstanarm, so look for that in 2017. We have a 600-page user manual that you can get for the Stan language by clicking on this link. We have an entire repository of Stan programs that have already been written in the Stan language called Example Models. We have a mailing list that's on Google Groups where you can ask questions about rstanarm or Stan or Bayesian inference generally. We have a conference coming up in January. That's one of the days it's going to be sort of a developer conference, but the 2 days previous to that, we're going to have training sessions in Stan that you can sign up for on Eventbrite. That'll be at Columbia in January, I want to say 17, 18, 19, something like that. And also you can email the email address that Eric mentioned at the beginning, not only with your questions about the presentation today, but also if you're interested in having commercial support or having us come out and do a more detailed training in Stan. Those are all things that we'd be happy to discuss with you. So with that, that's the end of the slides, and we have about 15 minutes for questions. And so hopefully Eric is ready to feed me some of those. Hello, Eric.
Oh, sorry, I was on mute. Can you hear me okay?
Yes.
Okay, great. Yeah, thanks a lot, Ben. That was awesome. We've had tons of questions that were coming in, and I was doing my best to answer some of them online. We don't have a ton of time to answer all of them, but what I was thinking we would do is that we'll try to get to a few now. Some of the questions are really good, and so I don't want to lose track of those. And what we'll probably do is, the last time, I wrote up a short blog post after we did the event with Andrew, where I posted the video and talked about some of the content. So I think what we'll do is we'll do the same thing here. We'll have the video available, and also we'll list out some of the questions we didn't get to that may be of interest to people, and then we'll sort of like answer them in a blog post form. And this way everyone can benefit from those. But in the few minutes that we have left, I think we have literally 10 minutes, let me start off with the first question, and that is there's this sort of the subtle issue that you alluded to, which has to do with expectations, taking expectations when making decisions. And I think it's often the case that like this word expectation in the common vernacular, it's not very descriptive. A lot of people who do work in machine learning or trying to use sort of optimization methods sometimes think that when they find an optima, that's somehow related to expectation. And of course, we know that's not generally true. So can you just say a few words about the importance of thinking in terms of expected values versus some kind of an optima of a function, such as we see in sort of posterior draws?
Sure. So there's three main uh, measures of a central value of a distribution. One is the mode, so that is the most likely value. And that's something that is most similar to what a lot of the optimization and machine learning and maximum likelihood produces. There's some function, and it finds the value of the parameters that yields the highest value of that function. But the mode is just one point, and it by itself doesn't tell you anything about other points that were almost as likely or maybe not close to as likely. Another concept is the median of a distribution, and so that's the value of the parameters such there's a 50-50 probability that it's less, 50-50 probability that it's more. But the one that we emphasize the most in Bayesian analysis is the expectation or the mean, and that is the average over all the draws from the distribution. And you can conceptualize an expectation as, okay, here's all the things that could happen, or here's all the values a parameter could take, and I want to take each of those values, multiply by the probability of that occurring, and then sum it all up. That's the process of taking an expectation. And so that's a much richer number because it takes into account everything that could happen with its associated probability rather than just what's the most likely thing to happen, because the most likely thing to happen in relative terms may have a pretty small absolute probability of happening. And there's a lot of other things out there that collectively have a larger probability of happening, even though individually they don't. And so when making like financial decisions, stocks and all this, you always want to be considering expected return, expected profit, these sorts of things, rather than just the best case scenario, the worst case scenario, things like that.
Great. Okay, thanks. There was an early question that had to do with overfitting. So the question is, how does rstanarm penalizes parameters to avoid overfitting?
So there's two aspects to this. One is putting a prior distribution on the parameters, and by default, rstanarm is always putting a prior distribution on each parameter. That has a similar function to specifying a penalization term in supervised learning. So oftentimes those are actually have a one-to-one correspondence. And so the prior basically penalizes the value for being different than from being too different from what you expected it to be before you did the analysis. So specifying a prior is one aspect of that. The other aspect of that goes back to what I was saying before about focusing on the mean rather than focusing on the mode. So really the root cause of overfitting in training data is focusing on the mode, which is very fragile. Even though it's the most likely in your one training data set, you could have an entirely different mode in another data set. And so that focus on the mode is really the root of the overfitting phenomenon. If you focus on the mean or the median, then your inferences are much less sensitive to the particular set of data that you have. We can do model comparison to choose models that take into account both their fit and their complexity. And we can predict, testing data, future data, if that's something that you're interested in, to see, what model has the best combination of fit and simplicity.
Great. There's a question regarding, when you were demonstrating the use of the rstanarm formula, you specified QR equals true, and there's a question about, can you give an instance? So is it always a good idea to set that a true, or are there times when you'd recommend not doing that?
The only time when I would recommend not doing is when you have strong informative prior beliefs about the coefficients. And so, if you believed that the size of the loan had, a coefficient of like negative 0.5, so you wanted to put a prior distribution that was normal, like negative 0.5, standard deviation of 0.1 on that particular parameter, then go ahead and do so. That's your beliefs. But under the reparameterization, the priors pertain to a transformation of the predictors rather than the predictors themselves. So they don't map on exactly to the coefficients as well. And so usually when you say QR equal true, that's for the case where you're happy just putting normal priors with location of 0 on everything, and then that is preserved when it does the transformation, and then it reverses the transformation at the end, so that the coefficients that you get back that you saw in the slides today do pertain to the predictors as you put them into the model. But that reparameterization step behind the scenes makes it a lot easier for Stan to go quicker and to get draws that have less dependence among them, so you can use fewer of them and still make solid inferences about the posterior means.
Great. The next question, I guess I can answer this, is, can I use all this shiny magic, thanks for calling it magic, by the way, to diagnose a model I've created with RSTAN, not rstanarm? And so the answer to that question is yes. You can use the shiny stan to pass it an RSTAN, a regular RSTAN object. One of the advantages of using the rstanarm object is that it knows your data, the Y. It already knows about that, and it also knows about the posterior predictions, or what we sometimes call Y-reps. And so when you do posterior predictive checking, if it's an rstanarm object, it will just sort of automatically pick that up. But if you use, let's say, an rstan object, you could just specify in the interface, it'll actually asks you to point to your data and to the replicated data. And once you set that up, it'll also perform these for you. The next question, there was, let's take this one. It says, does rstanarm support multinomial GLM?
No, not currently. So multinomial GLM is for a situation in which you have categorical outcome that is not ordered. So no, rstanarm does not currently support that. rstanarm does support models where the outcome is discrete but ordinal in the stan_POLR function. And we also have a branch where we've started to implement model for multinomial probit rather than multinomial logit. This allows the error terms to be correlated across choices. So look for that in the near future.
Great, and I think we have a time for just one more question, and it's a great question. It has to do with updating your model. So the question was, suppose you have some data and fit a model, then you collect more data. How do you proceed from there? Do you refit the model using all the data? Do you update? Is there some way to update the posterior or whatever? What can you sort of talk about this incremental updating strategy?
Right. So the incremental updating strategy is perfectly valid. So if you have a model with, data up until, last quarter or something like that, you obtain the posterior distribution, you can use that posterior distribution as a prior for the next quarter of data. And if you do this, this will often make it easier for Stan to run faster, in part because you only have to deal with a little bit of data at a time, and you still get valid inferences at the end that are conditioned on all the data because your interim posterior distribution was a function of the original data. However, that strategy is not implemented in rstanarm currently. So it doesn't have a good way to express the priors with enough generality to do that incrementing step. So if you were limited to rstanarm, after the next quarter, you would want to put all the data together, both from the past and from the most recent quarter. Use your original priors, use rstanarm, and you'll get back a posterior distribution. It might take a little bit more time, but it's the same posterior distribution mathematically is what you would have done if you did it in 2 steps with incrementing. But if you have a situation where you have like streaming data, you definitely want to check out rstanarm and maybe talk to us about how to do the incrementing thing more rigorously, because it can really make it possible to do analysis when, otherwise if you had to use all the data every time, MCMC would take too long for the amount of time you have available.
Great. Okay, well, thanks a lot, Ben. I think that's all the time we have. Thank you, everyone, for joining us. It's been great. We're going to continue doing these webinars, so stay tuned for future announcements. As I mentioned before, we're going to send out the materials, the video, and all of it, other information, or hopefully some more answers to questions that you posed in the form of the blog post. If in the meantime, if you want to contact us, please feel free to do so. You can use this email address, askus@stan.fit. Send us questions, comments, suggestions. We'd love to hear from you. And so we're going to wrap this up. Thanks again, guys. See you next time.